Hello divers, and welcome back to this series of 2 episodes dedicated to the physics of gas in scuba diving and its application to the main common scenarios we all face during our dives. If you missed the first episode, please find a link to it in the description. In this second episode, we will complete this analysis by examining some scenarios that involve the laws of Henry, Dalton, Charles, and Guy-Lussac. But given that the intent of this mini-series is to connect theory to practical scenarios, taking advantage of the additional experience gained since we completed our basic training, we will also explore some gas considerations that do not directly depend on these laws, but in some way play a role during all our dives. And let's start right from these last considerations.
As mentioned many times before, moving down towards the bottom means an increase in pressure, while going up towards the surface means a decrease in pressure. This implies that an object immersed in water is subject to different levels of pressure, lower at its shallower area and higher at its deeper one. All gases have the natural tendency to move toward the lower pressure zone, uniformly filling the container in which they are contained. This happens in any rigid container taken underwater, such, for example, our cylinder. But if the container is flexible, then the gas tends to move to the shallower area of the container, where the pressure is lower, leaving the deeper and squeezed zone empty. For example, every diver who has dived with a dry suit would confirm that standing vertically in the water, they felt a stronger pressure and vacuum effect on the feet compared to the torso or shoulders. The same effect happens at any second of any dive into our PCDs, making difficult for some beginner divers to realize where this gas is, complicating a lot the deflating, and sometimes even causing an uncontrolled descent. This is the reason why our trim in the water is so important for deflating our PCD and dry suit.
In the first episode, we have said that Boyle's law states that the volume of gas will vary in a predictable, non-linear, inverse proportion to the pressure. Increasing the pressure equals reducing the volume, and vice versa. In the opposite, but still predictable manner, the density will vary too. Density is defined as the mass in the volume, let's say a quantity in a space. As a general rule, forcing the same quantity into a smaller space or allowing the same quantity to expand in a larger space will change its density. Therefore, higher pressure will increase the density, while lower pressure will decrease the density. We could say that the density follows the pressure trends. The density of a gas is strictly correlated with the respiratory effort, which is why deeper depths make it harder to breathe. All divers who have tried to breathe a gas that contains helium will confirm that, at the same depth, the effort to breathe this mix is much lower than the effort to breathe air. What makes helium an easier gas to breathe is its characteristic of being less dense than air. This same lower density characteristic makes helium a poor insulating gas, approximately 70% less insulating than air.
Now finally, back to our laws and in some way also to the just mentioned diver's breathing is Dalton's law. The Dalton's law has a strictly correlation with depth and relative pressure variation, and it affirms that in a given gas, which might be composed of one or more gases, each single gas exerts its own pressure, and the sum of each of these pressures makes the total pressure of the given gas. Each single pressure is called partial pressure, and the law is often called the law of the partial pressures. Thanks to Dalton's law, each gas can be considered individually, establishing the depth limit according to its characteristic to prevent toxicity and narcosis, as well as to regulate the absorption and release of inert gases. In practice, for example, most of the time, a recreational diver will set the maximum depth and time to avoid decompression illness, narcosis, and toxicity, according to each gas contained in the available pre-filled cylinder, usually air or, if qualified, nitrox. In this case, the diver needs to know which are the maximum suggested breathable partial pressure of each of these gases, making sure to do not over them. But it can also happen that a diver starts by setting depth and time, looking only later for the necessary cylinder, which will be refilled according to the diver's specifications. In this case, the diver needs to fix the specific partial pressure of the gas involved, making sure the resulting gas is safely breathable for the specific fixed depth, and if necessary, also making sure which is the minimum depth from where the gas is breathable.
Not less important is that in the unlucky case that a diver needs to be treated in a decompression chamber, doctors will still use Dalton's law to ensure that each medical gas has the right partial pressure to be curative and not toxic, because, as we know, even oxygen can be, at the wrong partial pressure, toxic or unable to sustain the human life. Another law that our hypothetical doctor will apply together with Dalton's law is the Henry ones. The Henry's law says that a gas will dissolve into a liquid until its partial pressure inside the liquid is less than its partial pressure outside the liquid. When the inner and outer partial pressures are equal, no gas will move. And when the inner partial pressure is higher than the outer one, the liquid will release the gas. This means that by changing the partial pressure of the gas outside the liquid, we can lead the gas to move in one direction rather than the other. Different gases have different correlations with different liquids, and temperature and time also played an important role. Henry's law is also often called the law of the solubility of the gas.
So far, we have assumed that the temperature of the gas remains constant. This was an easier way to approach some physical change we have to face during our dives. Now, with the two laws of Charles and Guy-Lussac, we assume the temperature vary, keeping fixed one parameter among volume or pressure. While these laws are still very important for divers, they play a role not during the dive, but before and after it. The Guy-Lussac's law states that, at constant volume, pressure is proportional to temperature. In scuba diving, keep the volume constant means we are referring to some kind of rigid container. Having clarified this, let's see these three scenarios. The first, the cylinder refill. In this phase, a compressor pushes pressurized gas into the cylinder, resulting in increased temperature, which itself results in increased pressure read by the pressure gauge of the compressor. In other words, in this phase, the inner pressure of the cylinder is higher due to the higher temperature, but it will drop a little when the cylinder temperature decreases to the ambient one. This is why cylinders are refilled in a water pool, and because the cylinders are filled to a slightly higher pressure than needed, for example, up to 220 bar, which will decrease to approximately 200. Second scenario, carrying the cylinder to the dive site. The pressure of a cylinder left in a car under the sun during a summer day will increase due to the temperature inside the vehicle. Aside from the potential risk of an explosion, the other risk is that if we measure the cylinder pressure without allowing its temperature to drop to the ambient one, we can have an altered and misleading value, higher of what will be really available when jumping in water. The third scenario. The trick used when refilling cylinders plays now against us. In that moment, we refilled cylinders into water to keep control of the process. But after a short time since we jumped into the water to dive, even if it's not particularly cold, the cylinder pressure can drop due to the reduced temperature. If the cylinder was left in the strong sun for an extended time, the difference between the supposed pressure and the real one can be significant.
The Charles law says that at a constant pressure, the gas volume will vary depending on the temperature. Higher temperature equals to higher volume, while lower temperatures reduce the gas volume. It might happen that at the end of the dive, back on the surface and wearing our dry suit, we feel colder than usual. Of course, this may depend directly on the outside temperature, but it can also be the consequence of the volume of the inner gas in our dry suit, particularly reduced by the cold temperature. It amplifies the vacuum feeling typical of the dry suit.
We have discussed all these laws separately, but they often find practical applications working synergically. And of course, all these laws are fundamental in decompression theory and the relative mathematical models used in our diving tables and computers.
Here ends this series of 2 episodes dedicated to the physics of gas in scuba diving and its most common applications. Thank you for watching. If necessary, find in the description a link to the first episode of this series, and also a link to download a written summary of this video. Remember that by clicking on the bell and by subscribing, you will be informed about new videos, while by sharing and giving a like to this video, you will help to spread greater awareness among divers.